Okay, so I would like to welcome all of you once again for another edition of the NSF Wednesday Colloquium. It's a pleasure to have Professor Surajit Dhara joining us for this session from his office at University of Hyderabad. And it's a pleasure to welcome you, Professor Dhara. Before I go on and formally have my colleague, Professor Sushil Majumdar, introduce Professor Dhara for the talk, I would like to mention a few words about the Wednesday Colloquium. Actually, the Wednesday Colloquium forms sort of the oldest part of science communication that we have within the institute. Every Wednesday at 4 p.m., all the scientists under the roof get together and listen to sort of lively expositions of the latest and contemporary science from experts from all around the world. And due to the pandemic, it's actually kind of a blessing in disguise. We get experts from all around the world sitting from their offices and homes and giving talks in the right time zones. I actually also would like to thank my previous colloquium coordinators, one of whom is going to introduce Professor Dhara. This is Professor Sushil Majumdar, who has been instrumental in putting many of these things for the coordinators after him, making life easy for these coordinators after what he did as a colloquium coordinator for this series. So Sushil, over to you, and I'll hope you introduce Professor Dhara today. Yeah.
Thank you very much, Jyotishman. Thank you for your very kind and generous words for me. I should mention here that the coordinators prior to me made a job much easier for me and those following me. So that's what we are all reaping the fruits of. So welcome everyone and good afternoon to all of you. It's a great pleasure to introduce to you my good friend, Professor Surajit Dhara. Surajit is currently serving as a professor in the School of Physics, University of Hyderabad. Surajit's research interests are, generically speaking, soft condensed matter physics to do with colloids and liquid crystals. And more specifically, regarding these topics, he studies phase transitions, topological defects, electrokinetics, optical resonances, and rheology and phenomena relevant to all of these. Over the years, Surajit's research has been amply recognized with some very famous accolades. To start off with, he won the Michi Nakata Prize by the International Liquid Crystal Society in 2010. In 2012, he was awarded the N.S. Satyamurthy Memorial Award in Physics for Young Scientists. In 2016, he was recognized by the Swarnajayanti Fellowship Award. And most recently, last year, he was given the Shanti Swarup Bhatnagar Award. With that very short introduction, I would like to invite Surajit to present his colloquium. Thank you for joining us, Surajit. It's over to you now.
Okay, at the outset, let me thank Sushil and Jyotishman for the invitation, and also all of you for attending this lecture. And also thank you for the kind introduction which Sushil gave. I will switch off my video probably while I'm giving the talk. Okay. So, yeah. So today I'm going to talk on colloidal squirmers in a liquid crystal. I'll go rather slow. So in fact, you may stop me if needed. And in fact, I would like to have interaction during the talk also. And you can stop me anytime as you feel. So the title of the talk is Colloidal Squirmers in a Nematic Liquid Crystal. We know the squirmers are basically a model or artificial microswimmers, and they generally swim in fluids with low Reynolds number. And their flow is usually kind of the surrounding flow around the microswimmers are usually can be understood based on the Stokes laws. So therefore, the flow they have surrounding the microswimmers are kind of Stokes flows. The motivation, so the work which I'm going to today present is that artificial microswimmers actually, and they are in liquid crystal instead of having them in isotopic solvent, which we usually see. So let me show you one slide about these natural microorganisms, which are actually the microswimmers. This is what the motivation behind such kind of work. And we know that in our daily life, we encounter several microswimmers, for example, algae and bacteria. This is the chlamydomonas algae, which you can find in fresh water, and we can see that when you disperse them in water, they continuously move, okay, in different directions. Similarly, this is a bacteria. This bacteria is E. coli bacteria, and this bacteria is, as you know, that this causes our stomach upset, all kinds of problems. And this E. coli bacteria also, they swim. So they are natural microorganisms which are actually swimming. They're also called microswimmers. These are true microswimmers. Now, there are several important aspects of these microswimmers. If you see these microswimmers, though they are moving, and mostly because of in search of food or probably because of reproduction, whatever the reason, but they are continuously moving in the system and consuming energy from the system. And this is a system which is basically a non-equilibrium system. And if you have a large number of such microorganisms in a place, their hydrodynamic interactions and often their collective motion is a subject of very intense study in the present days. Now the point is, if we want to study them in a controlled way in the laboratory, it is very difficult to handle such algae or the natural micro swimmers like bacteria or algae. The question is, can we design artificial microswimmers so that we can study them in the lab in a controlled manner? Because as I said, the most important point is that when we have a large number of such particles, their collective motions due to hydrodynamic interaction or many other interactions is going to be the very, very important aspect. Now in this talk, I will present some results on artificial microswimmers. I will show that we have actually created artificial microswimmers. The microswimmers whose directional motion is controllable by external field. In this case, these microswimmers are actually self-propelled, okay? And the artificial microswimmers which I am going to talk about, they are artificial and they are actually driven from the external forces. But the important point is that still the different system, we can find some sort of or the mechanism of the swimming. I will show you that more or less similar to what we actually observe in case of the natural microswimmers like algae or bacteria. Therefore, the artificial microswimmers could be very, very useful for understanding some of the fundamental aspects of these microswimmers. Now, coming back to this, so these microswimmers we have actually created in liquid crystals, and so before going into the actual microswimmers, let me give some brief introduction about liquid crystals. So as in the previous slide, I have shown that the microswimmers are actually moving in a fluid, which is isotopic fluid like water-based, some solvent with some food. But in this case, in place of a isotopic solvent, we use liquid crystals. So liquid crystals are basically it's an intermediate state between a solid crystal and isotopic liquid. We know that in the solid crystals, if it is made of some sort of anisotropic particles, the molecules, they have both positional as well as they have orientational order. Okay, and in the isotopic liquid, we can see that both positional as well as the orientational order is destroyed completely. But there are many organic crystals which are made of mostly safe anisotropic molecules like this kind of elongated molecules. One example of the molecule is this. You can see it's a simple organic molecule. Often, when you heat them, instead of going directly from crystal to the isotopic liquid state, they go through intermediate state in which they retain their orientational order of the long axis, but they lose their positional order. That is a state what we call the liquid crystals. So in the liquid crystalline state, since the name says liquid crystals, it is obvious to sort of imagine that this state will have some properties of crystals, solid crystals, and also some properties of isotopic liquid. And in fact, there are so many liquid crystals now known, and one of the simplest liquid crystals is called nematic liquid crystal, in which we have only orientational order like this. So the molecules, on an average, they tend to orient in a specific direction. The direction we define what we call is director, and normally defined by n cap. See, unit vector, it's a direction, okay? Because you can see that these molecules on an average align in the director n, because they have some left, right, or tilt there, but on an average they are along this direction. Whenever I will use this n cap, which means the average alignment direction of the molecules. Now, Now, if we heat or cool the solid crystal to isotopic state, it will always go through this kind of liquid crystalline state. For example, one example of the molecule is given here. Now, those who have not seen it, there are some students that the liquid crystal room temperature, which is used in all your laptops, cell phones, or even computers, everywhere, they are room temperature. Their room temperature, the liquid, the turbid liquid, you can see that because they scattered strongly light. And this example of a room temperature nematic liquid crystal. But if you look at part of it, their molecules on an average are having orientational order in a specific direction. Okay. Now, what is beautiful about the liquid crystal is that they have all physical properties are tensorial in nature. For example, if you have a uniaxial liquid crystal, nematic liquid crystal, we can define at least two diffraction indices with polarization parallel to this director. So this parallel symbol means the polarization parallel to the director. We measure what is called n parallel, which is basically or equivalent to extraordinary diffraction index of the uniaxial liquid crystal, and perpendicular to this director, we can get NE extraordinary or n perpendicular. And this diffraction index typically it can vary from 0.1 to 0.4. Similarly, it has a dielectric anisotropy, meaning that if we apply electric field parallel to director, we measure epsilon parallel, and we can also measure perpendicular, and difference between these two quantities is called delta epsilon. And this delta epsilon is of the order of, it could be 55 to 50 or so. And the conductivity anisotropy is also anisotropy. Okay. Therefore, we can see that physical properties of liquid crystals are anisotropic, and these are the typical properties of a nature of solid crystals. Whereas, since it's liquid crystal, it also has viscosity. Unlike isotropic solvents like water, you have only one viscosity. In case of liquid crystal, we can have three different viscosities depending upon how we shear. For example, we shear a liquid crystals having three different orientation between two plates with respect to the shear direction. So we have a velocity gradient direction along z, velocity of direction in the y, and there is a neutral direction. So we can get three different viscosities, eta 1, 2, and 3. And this typical viscosity for the liquid crystals varies from 10 to 100 millipascal second, which is more than 10 to 100 times larger than conventional viscosities, I mean, like the viscosity of water. Now, another important aspect of liquid crystal is that they are also elastic because it has viscoelastic material. Now, the elasticity comes from the curvature. So, if we have uniform, so this represents ellipsoid represent the molecules. If you have uniform deformation, there is no elastic energy cost. But if you want to create elastic deformation, like this we call splay, which has a non-zero divergence. You can twist, non-zero curl, and also a bend. This costs elastic energy, and the typical elastic deformation energy can be written in this fashion. And what is important, you can see that the elastic constant associated with these deformations are called splay, twist, and bend elastic constant. And the typical values of these constants are 10 to the minus 12 Newton. Please note that dimension of this elastic constant is the force. So it is extremely small. This is why we can apply very small electric field and create such deformation. This is what is exploited in all the LCDs. Now, those who have seen liquid crystal under optical microscope, one very interesting and fascinating aspect of liquid crystal is that you can observe the topological defects in the medium. For example, this figure in this picture, I show that this picture is taken in an optical polarizing microscope, meaning this is a normal microscope, but you see the sample between two glass slides using a cross polarizer analyzer orientation. So very often you will see across a very colorful texture with some dark lines moving around here and there. But there are some points like these where the four lines are meeting. These are the points. These are called the defects. The defects are basically a point where the orientational order is destroyed, meaning the orientational order is zero. But of course, far field you have a slowly varying elastic variables. For example, if you look at a defect, which is the center of this point is the defect, and the core of the defect is typically of few nanometers, and you can see the dark lines. The dark lines comes because of this polarizer analyzer. Now these defects, like in XY model, we can define the strength of the defects. This is basically the winding number in XY model. So how do I define? For example, if I go around this point 2 pi, and if these molecules or the director the average orientation or direction of the molecule also rotated by 2 pi, then the defect is 1. If alpha is 2 pi, then it is 1. If I go, let's say 2 pi, but the alpha is pi, then it is a half defect. Let me show you some typical example of the defects which we usually see in liquid crystal. So these are the called point defects, and here we can see that this at the center in this point is the core of the defect where the orientational order is destroyed. In fact, we cannot define the orientation at this point. And so this is like a radial hedgehog, okay? And these lines represent this molecular orientation, not the molecules, but the average orientation of the molecule. So this is called radial hedgehog, and this is a point +1 strain. Similarly, this is a hyperbolic hedgehog. We can see that the defect, the magnitude-wise they are same, but the sign is -1. Means this sign we can find out by going and clockwise along this. If the director rotates clockwise, then it's a plus. If the director rotates anti-clockwise, then it is a -1. So this is a typical schematic diagram of the molecular orientation around the defect points, which are sitting in the center of this images. Now these are usually point defects, and which we see here, for example. It is also possible to have a line defect in which the defect strength is half. You can see here in this structure, in this diagram, that if I go 2 pi around this point, the director rotates by only pi. Therefore, pi by 2 pi, it's a half defect. Now, depending upon the sense of rotation, it could be plus or minus half. Okay, and these are the typical defects we very often see under optical polarizing microscope when you deal with a nematic liquid crystal. Now, the question is that, so the point is that I'm going to talk about micro swimmers which are swimming in liquid crystals. So I gave some basic or information or some kind of fundamental information about the liquid crystal, which is needed to know the further experimental results. Now, coming back to this, since the microswimmers are kind of foreign particles to the liquid crystals, because liquid crystals are organic molecules, and microswimmers here it's a colloidal particle. Now, the question is actually what happens when we put or throw the foreign particles in uniform liquid crystals. Let us give me some example that the lines represents the average orientation direction of the molecules, or what I call the director. So this is uniform orientation of nematic liquid crystals. Now, when I put a foreign particle in the medium, and what happens? It creates a. One can calculate the elastic energy, which is given by the average elastic constant K into the radius of the particle. And since the liquid crystal also has a surface tension, we can get a equivalent surface energy, and the equivalent surface energy of the liquid crystal onto the surface is given by WR square, where W is the surface energy per unit area on the particles. So what we see is that when we put a foreign particle of some size, it creates elastic distortion. It also there is anchoring energy, and there is elastic energy. Now, elastic energy increases with the size of the particle, but the anchoring energy increases quadratically with the size of the particle. Now, if you have a nanoparticle, a dispersed liquid crystal whose size is very, very small, therefore the elastic energy is actually larger compared to the anchoring energy because it's square. Therefore, the elastic energy basically overtakes the anchoring aspect, and it does not create any elastic deformation in the medium. What do I mean is that if you put a nanoparticle in liquid crystal, it does not create sufficient elastic distortion in the medium, which means the medium remains almost uniform because the elastic energy is larger compared to the anchoring energy. But suppose I have a bigger particle, the microparticle, and I disperse in this medium. Then what happens? That the anchoring energy now is proportional to R square. The anchoring is much larger than the elastic energy. And then what happens? The molecules, the lines represent the molecular orientation, which are anchored to this particle. They want to retain their orientation. For example, this is a particle, and this particle is treated chemically to promote some kind of vertical alignment of the molecules. Therefore, when this particle is thrown into liquid crystal molecules are perpendicular to the surface. Now, this particle you can sort of assume that it is a source of a defects having +1 because this is coming radially out. So basically a radial hedgehog. But now topological charge conservation demands that we should have another minus charge in the vicinity of this particle to have total defect 0 because we cannot create the defect, right? So what do I mean is that if you throw a microparticles, Microparticles in the vicinity wants to retain its orientation, but in the far field it's uniform. Therefore, that the particle will induce a hyperbolic -1 Hedgehog defect in the vicinity of the particle. Therefore, putting a particle, we can create a defect and anti-defect. So you can say this anti-defect is a defect. So defect and defect pairs are created the moment you disperse a bigger particle. That macroscopic, I mean the micron size particle. Now, this point defects, if we push towards the particle, this point defect can also open and it can become a ring, and what is called as a Saturn ring, because topologically the point defect of -1 and is equivalent to a ring of defects of -12. Okay, therefore this conversion from a point defect to a ring defect on the particle is possible. Now, another interesting aspect of this defect is that these defects are also called elastic dipoles and quadrupoles. The analogy of the analogy with the electrostatic perspective. In fact, it was shown by Tom Lubensky for the first time that if you analyze the transverse component, meaning that if, let's say, this is z-axis, you look at in the xy plane, the director component in the nx and ny will have the similar symmetry of that of a electric field lines of a charge in a electrostatic field. And similarly, he also showed that it is also possible to have this elastic quadrupole, meaning that symmetry of these xy components of the molecular field has the same symmetry of that of a electrostatics. So this analogy comes from the electrostatics, and these are called elastic dipoles, and these are called elastic quadrupoles. So the particle dressed with the defects is called elastic dipole, and the particle dressed with this ring defect is called elastic quadrupoles. So another possibility is that in this case I said that the molecules are actually ensured by some chemical treatment to be perpendicular on the surface. But suppose I treat some chemicals and make the molecules to be parallel to the surface. In that case, what we see that there are two half defects, basically which are antipodal defects induced along the far field director. So these are basically two half defects, and these are called bosoms. The particle together with the defect is called bosom, and as far as I know, this term was basically introduced by Marmin, and it was taken from some poem which means some dangerous animal. Anyway, the point is that when you put a foreign particle with a well-defined surface orientation of the molecule, we can induce what is called a elastic dipole or a elastic quadrupole or a bosom. So let me show you how this particle looks like in optical polarizing microscope. The dark images here on the left side are the images taken between two cross polarizers of a spherical silica particle. We can see there is a point defect clearly here near the particle, which is here. Similarly, we can see that there is a ring defect around the particle and the equator, and also there are two dark points. These are half defects along the far field director. In fact, in the bright field image, we still see the point defect near the particle. And in the beginning, it was a uniform nematic like this, but the moment you put this particle, the particle induces this defect, which is -1, because the particle as a whole acts as a +1. Similarly, this is a ring defect. As I said, that this point defect can be pushed and they can be opened as a ring defect. So therefore, the conversion from this to this is possible. And these are bosoms. Since these are surface defects, they are very, very close to surface, and they are merely visible. And in fact, if the particle is big, sometimes we may be able to see this defect even in the bright fields. Okay.
Surajit.
Yes.
Surajit, a quick question. You have been using a term far field. What is far field in this context?
Yeah, in this context, good question. So when you look at the particle, let me go back to this. See, this is the near field. I mean that the region near to the particle, you see there is a deformation. Now, if you go to far away from the particle, this director is uniform, right?
Yeah.
So area is uniform, but only the near field that there is deformation.
Yeah, but is there a quantitative estimate? I mean,
no. Normally, this particle size, if you see that, you can see the distortion this is a point defect. You can see that it's half the particle size, the region where you can see the distortion. Okay, so this
Okay.
in the sense the far field and near field means that very close to the particle and very far from the particle, because far from the particle the director is uniform, there is no deformation. It's only near field, near the particle there is deformation.
Okay. Thank
Okay?
you.
Yeah. Now, now the question is, if we apply electric field to these particles, then what happens? In fact, as you know that this when you disperse colloidal particle in electrolytes, and there is something called electrophoresis. So the question is similar thing happening in case of these liquid crystals? And one point to remember is that liquid crystals are organic material, and whatever we do, we cannot remove completely the ionic impurities from the system. So therefore, there are always some ionic impurities which are inherent in the synthesis process. They are present, and they cannot be removed. Therefore, liquid crystals are dielectric, but they are weakly electrolyte in the sense the moment you apply some AC field or the field, the ions they tend to move in the field direction. Now, so let us. So since I am talking about electrophoresis, let me tell you what happens in case of a linear electrophoresis first. Suppose I have a charged particle in some isotopic solvent, and I apply, which is of course electrolyte system, and if I apply electric field, then this since the particle is negatively charged, then it will induce the positive charge in surrounding, and therefore there will be a charge cloud, and this charge will drag the fluid in this direction, and therefore, and the particle will be moving in the opposite direction of the field, and that the slip velocity around the particle is given by this expression where zeta is the zeta potential, and we can see the slip velocity is proportional to the field E. Okay, and this is standard linear electrophoresis. But there is another kind of electrophoresis, what is called non-linear electrophoresis, where the particles are not charged, but they are polarizable, meaning that we can actually create a polarization in the particle by applying field. For example, I have, let's say, a metal particle which is highly polarizable. The moment I apply a field, there is a polarization in the metal particle that induces opposite charges in the surrounding. Now that induced charge is proportional to the electric field. Therefore, the zeta potential which is created surrounding the particle is due to the field. Now those charges they respond to the field. Therefore, the slip velocity is proportional to E square. So if I put zeta equal to EA, so I see that slip velocity around the particle is E square. Therefore, it is polarity independent. Therefore, I can pump the fluid surrounding the particle by a AC field. This is very interesting. Now, if the particle is spherical, we can see that the flow surrounding the particle is symmetric. So there is a 4-arc symmetry of the flow in the surrounding the particle. Therefore, though there is a local flow surrounding the particle, but this flow, since it has a symmetry, it will not create any motility in the particle. What I mean that the particle will not be able to move, and though there is a flow surrounding the particle, and this is called induced charge electroosmosis, and the phenomenon is called also induced charge electrophoresis. Now, so this is the standard electrophoresis, linear or electrophoresis, when you put some particles, either charged particle or polarizable particle, in isotopic solvent like water, with of course some ions, I mean some positive and negative ions. Now, what happens when you put foreign particles in liquid crystal? Now, as I said that the moment you put a foreign particles like silica particle in a liquid crystal, it induces a point defects or ring. For example, I saw you some movie. You see this particle has induced a point defect, yeah, in front of it. Now, when we apply, so this is a sort of video taken under cross-polarized, optical polarizing microscope, and this arrow shows the direction of the far field director, okay, or the molecular orientation in this direction on an average. Except the close to the particle, everywhere this alignment of the liquid crystal is uniform. And now, when we apply this electric field, you can see that the two particles are actually moving, and they are moving keeping the point defect forward. See, this is the point defect here, and this is the point defect here. So this is the motion of the particle under electric field parallel to the director. So what we see, the particles, they induce a defect, and with the defect they move in the director or the average far field direction. Now the question is why these particles are moving. So if you see, I will just explain in the next slide. The velocity of such particle is found to be proportional to E square, which means this is a nonlinear electrophoresis. And moreover, the velocity also depends upon the conductivity and anisotropy of the medium, liquid crystal medium, and also dielectric anisotropy of the medium. I have introduced already these two quantities in one of my previous slides. Therefore, we can see these particles are moving because of the anisotropy in the conductivity, dielectric properties, and also it is proportional to E square. So E square means it is a nonlinear phenomena, and it also depends because of this anisotropy in the physical properties. Now let us see actually why such particles are actually moving. Now this is a schematic diagram of the lines represent the dielectric field. So when you apply electric field, the impurity charges which are present in the liquid crystals, they move. They cannot penetrate the particle, and in fact they are collected around these particles, and this dark one is the point defect. What we can see that when there is a flow, surrounding flow, which is given by these arrows, the symmetry of the flow is broken due to the presence of this point defects. So here, the point defects introduced by the particle in the medium breaks the symmetry of the surrounding flows. In fact, that can be tested out. So this is one experiment done by Oleg Lavrentievich long ago. So they disperse these quantum dots, fluorescent quantum dots, and you can see when they apply field, you can clearly see these quantum dots actually there is trajectory they can track, and you can clearly map the flow. In fact, here it is shown the direction of the flow direction also is shown. So while the charges are moving, they're dragging the fluids, therefore they're dragging also the quantum dots, and that is how this trajectories can be created. What is important point here is to note that yes, there is a symmetry breaking in this plane, along this plane, in case of a particle having point defect. Therefore, this particle is motile in this direction, in the forward direction. Therefore, unlike in nonlinear electrophoresis, the particle has to be asymmetric to break the surrounding symmetry of the flow. In this case, though the particle is symmetric, but the broken symmetry of the medium is responsible for creating the asymmetric flow surrounding them, and which sort of makes the particle motile in the forward direction. It moves forward or backward depending upon where is the point defect. It's here or here. Now, I also talked about two other different types of defects. They are called quadrupolar defect, in which they have a ring defect, and also boson defects, where you have two surface defects, which are minus up, minus up. Now, if you see in this case, again, these charges are also in motion, and they drag the fluid, but the flow of the fluid surrounding these particles having certain ring is a symmetry. Symmetric. You can see there is a perfect symmetry of this flow surrounding the particle, which is also traced out by these quantum dots. You can see there are sort of vortices, and they are very much a symmetric flow. Therefore, this is again this velocity, a sleep velocity around this particle is also proportional to E square. Now, but this particle is not motile because the flow surrounding the particle has a 4-arc symmetry. Therefore, the particle is not motile. Similarly, when you have a this boson defects, surface defects, the antipodal surface defects here, again the flow is reversed compared to these defects, but they are also still symmetric. And as you can see here, the trajectories clearly show that they have sort of 4 vertices, and the flow is symmetric along any 2 planes you can imagine. Therefore, the particles with quadrupolar symmetry or the boson particles, they are not motile even if you apply electric field. So this, to summarize, that particle having point defects will be motile, and that motility will be bidirectional, meaning either they go left or right along the director. If they have a quadrupolar symmetry or the boson particles, they are not motile. Okay. Now, what we did, we actually created the motility. We broke the symmetry. Since we cannot do much with this in the medium, the moment you induce this kind of defects, we cannot break the symmetry of the medium. What do we did? We actually introduced asymmetry in the particle. We actually designed or created metal dielectric genus particle. So these particles are actually silica particle of 3 micron. Half side of the particle is metal coated, titanium coated, and then after coating the metal, so this is a side view. You can see half side is dielectric, half side is metal, and then on the metal again we coat another thin layer of 10 nanometer silicon dioxide to make this particle surface sort of homogeneous, in the sense that it's overall silica. So the outside medium will not see the metal, it will only see a silica surface. Now, to give a specific alignment of the liquid crystal molecule onto the surface, we also coat some sort of organic molecules which are known as DMOAP. This is basically this kind of change interact with the molecules and gives rise to a desired orientation of the molecule as we want. Now, this particle, as you know, that they are called genus particle and having two defined phases. In fact, they have different properties here, electrical properties. Now, these particles are not very difficult to make. Basically, we start with a silica particle of 3 micron. Then, using E-beam evaporation, we can make a give 35 nanometer of coating, and then on top of that, to make it a overall silica surface, again we coat silicon dioxide or silica thin layer, and then we take the particle out, and we have a genus particle. These particles, after coating these organic molecules, we disperse in liquid crystals, nematic liquid crystals. Now, this is so now I told you that I have already shown that if you have a silica particle, there is a point defect and it breaks the symmetry, and the particle is in motion. Now, what we did, we first introduced, we took genus particle, which is a metallodielectric genus particle, and again we introduced some kind of point defects, basically this kind of defect. So this would be, of course, the metal surface is not shown here. So this is a metallodielectric genus particle, and the geometry is that the field is along the z-axis, and we see in the xy plane, and you can see that this metal surface is shown by the dark sides, and the reds are basically the point defects. So the moment you apply electric field, what happens? I saw in this movie. We can see that the genus particles, the dark hemisphere is basically a metal coating. They move either in the left side or in the right side, and the field is perpendicular, and this direction is the direction of this molecular orientation. So what happens with these particles? Those particles are moving left side. In their case, the point defect is in the forward. Those particles are moving in the right side. In their case, the point defect is just in the front, in the forward, in the right side. Therefore, so again, the basic mechanism is the same, that this point defects break the symmetry. What is the difference? Difference is that when you measure the velocity of this genus particle and a non-genus particle, we see that the velocity is proportional to E square, as expected in a nonlinear electrophoresis for a non-genus particle. But the moment you have a genus particle, its velocity is much larger for a given field. Therefore, the velocity of this genus particle compared to this non-genus particle is much larger. But the similarity is that they have still the bidirectional motion. This meaning that the particle only moves left and right. Another question is that, can we control the motility of this direction? Can we control or steer the direction of motion? Can we control or pilot the direction of the motion of the particle? The answer is possible, but not for the particles with having point defect. Now, I'll show you some results on a quadrupolar genus particle. These are basically genus particles, but these particles are dressed with Saturn ring defect. Okay, that means the point defect is forcefully opened and made a ring defect along the equator. Now, as I said, that the flow of the fluid surrounding the particle is symmetric. Therefore, if you have a non-genus particle, the particle will not move. But because of the genus particle, when you apply the field, and again I see in the xy plane. So these movies are taken in the xy plane, are seen in the xy plane and field in the z direction. So the field is out of plane in this movie, and this is the average direction of this liquid crystal molecule, or what we call a director. Now look at this particle. This particle is having metal hemisphere up, and down is the dielectric hemisphere. If you can see, I do not know if it is clear, the ring is still visible. You see, there is a dark point here and in here. That means the ring defect is perpendicular to the director as expected. There is a ring. So all the particles are actually dressed with a ring defect. Now when we apply the field, you see this particle is moving perpendicular to the director. This is director direction, and this is moving perpendicular and making the metal hemisphere forward. Similarly, when the metal hemisphere is downward, the particle actually goes down in the opposite direction. Now, what is remarkable is that I already told that the particles with quadrupolar symmetry, non-genus particle, they are not motile. But see what happens the moment we make a genus particle. That means we break the symmetry of this particle itself, the particle becomes motile. Not only that, the moving direction now is different depending upon this metal surface. Now look at another video. In this case, the metal dielectric interface is some angle with respect to this director. Now when you increase the field, you see the particle is moving, making the metal dielectric interface at some angle. Okay, at some angle. Similarly, in this case, the orientation is slightly different, and we can see that the particle actually move in this direction. Again, it is making some angle with respect to nearly 45 degree with respect to the far field orientation. So in this case, the metal hemisphere is downside, but again, so if you apply the field, you see it moves in the opposite direction. Similarly, in this case, the metal hemisphere is this side, and we can see the particle actually moves in this direction, nearly 45 degree with respect to this horizontal direction. So what is important is that the particles in a plane can be transported in different directions depending upon the orientation of the metal dielectric interface. To summarize, what we find is that if we define a Janus vector, which is basically a perpendicular to the metal dielectric interface, which is S, Janus vector is S, and N is the far field director. Now we can actually change this angle phi between the Janus vector and N. So different orientation of the Janus vector or the particle is possible in a plane by just rotating this particle along this axis. Okay, they are defined for angle of phi. We can see the different kinds of orientation of the Janus vector. Now this is a relative coordinate, meaning that by relative I mean that with respect to a common origin. If you apply a field which is into the which is basically coming out of this plane, and the far field directly in this direction, we can see that when the particle which is moving in this direction is facing a dielectric hemisphere. Okay, but the particle which is moving perpendicular to the director is facing the metal hemisphere. Similarly, the particle which is going down the metal hemisphere, but at intermediate angle, you see they have metal hemisphere or the metal dielectric hemisphere making some angle. So what is the important point here is that depending upon the choice of the orientation of the Janus vector, the particles can be transported in all directions. Therefore, we say this is omnidirectional motion. This is remarkable because we are applying unidirectional field. So field is always perpendicular. You see, the point is that field is always perpendicular, but the particle goes in different directions because of the orientation of different Janus vector. So this is something very, very special, and this you will not see if the medium is isotopic medium like water. Okay. Therefore, we can say that depending upon the choice of the appropriate Janus vector, we can have a omnidirectional transport of the particle in a thin film of liquid crystal. Now, not only that, in fact, by changing the field amplitude, we can actually remote control the direction of the motion. For example, this is one particle, and the Janus vector is this direction. Okay, and if I apply field, you will see I will change the field here between 1.5 to 2, keeping the frequency fixed. You see, the particle is actually, when the field is 2, I change it to 1.5. The moment I change the field, the particle is changing its direction in different places. Again, I change the field, direction of motion is changed when the frequency is fixed. Now, if you look at this sort of summary of this trajectory, is that the point wherever I am changing the field amplitude from some value, let's say 1.5 to 2, there is a change of direction of the particle. Therefore, I can actually control the direction of motion by changing the field amplitude, that too remotely. Okay, this is very important that we can actually have a controlled transport. Okay. Now, if I do this experiment, for example, for a fixed orientation of the Janus vector, and let's say I started with a fixed field. For example, if I apply 1.1 volt per micron, the particle will continue to go in this direction. If I, let's say, apply higher field, what we see, the particle goes in different trajectories. In fact, one can measure the angle of this trajectory with respect to this n of the director. So this is the angle with respect to this director. We can see that the angle, the theta, decreases as you increase the field. So the low field, it is going here, and the highest field, it is actually close to this director. Therefore, by controlling the field amplitude, we can change or tune the angle of motion, or change the theta. So apart from that, we can also control remotely the direction of motion by changing the frequency. So this is again, here I will show you that the frequency will be changed between two numbers, 30 to 50 Hz, keeping the amplitude fixed. So you can see the particle is moving in this direction, but the moment I change this frequency 50 Hz, if you look at the change here, 30 to 50 Hz, whenever I change the frequency, the direction of motion is changed. And I'm changing between two values. 30 and 50 recursively, so that I just show you that yes, it is actually a controllable sort of transport. Okay, wherever I change this frequency, direction of motion is changed. Again, look at the summary of this trajectory. We can see these are the points of the places where I have changed the frequency from 30 to 50 hertz, and recursively this has been done. And we see we can guide the particle in a zigzag manner just by changing the frequency. Again, to summarize that, we can show that if we have a fixed field amplitude and just change the frequency, we can, depending upon choice of the frequencies, we can transport the particle in different directions. So if you measure the angle theta of the trajectories with respect to the director n, and we can see that as we increase the frequency, the theta, the angle of the trajectories are also increasing. Therefore, it's linear. Therefore, it is easy to tune the angle by tuning the frequency very precisely. This is very remarkable because by changing the frequency and field amplitude, we can control the direction of motion at will. Now, I show you another interesting experiment that, let's say I have a target. This kind of transports are very useful for targeted delivery or so. So this is, I have a target. Now I continuously guide a particle just by varying the field amplitude from, let's say, from 1 to 2 volts per micron at a fixed frequency. So the field is perpendicular to the plane and director is given by this arrow. Now see, I am just increasing the field continuously. My target is fixed, so I can actually guide the particle to the target. This is indeed remarkable because this guiding, I mean, see, the point is that why it is so important is that yes, we can drive a particle by field, but that is either in the field direction or the gradient of the field direction. But here, field is perpendicular and the motion is taking place in a plane which is perpendicular to the field. This is very, very important. Now the question is, how do we understand that why such kind of controllable motion or the motility is possible in case of liquid crystal? This can be understood if we look at this velocity component or the velocity dependence on the field and frequency. So in this figure, what we have done that we have measured the velocity of the particle. Let's say this particle has a genus vector oriented in this fashion, and so this particle will move in some direction with the velocity. The velocity has two components, Vx and Vy. So if we plot separately and Vx and Vy, we can see that the velocity along the this Vx and Vy with respect to the director, okay, measure with respect to the director n. So if we see that the velocity along the x direction is higher than the y direction, okay. So you can see the slope of this line is along the for the Vx is greater than the Vy. Now, when we change the field, let's say from 4 to 5 volts, for 4 to 5 volts per micron, okay. The point is that the velocity is sort of proportional to e square, which confirms that this is a nonlinear electrophoresis. And secondly, that velocity x component is larger than the Vy. Now, if we change the voltage, field from 4 to 5, what we can see? Since Vx having larger slope, the relative change in Vy is going to be Vx is going to be larger than the Vy. Therefore, we can see that we can actually change this theta. So because when we go to 4 to 5, we can see the Vx is changing much larger than the Vy because of the larger slope. Therefore, we can have a corresponding change in the angle theta. That means the relative sensitivity of the velocities at the surface is responsible for creating this motion. Whenever I am increasing the field or decreasing the field, the velocities around this particles on the metal and the electric surface, the relative magnitude are changing. Okay, that is why the particle actually is steering or changing the direction of motion. Similarly, the frequency dispersion also can be understood. This is a typical sort of frequency dispersion is seen even in isotropic fluid, that in the low frequency the velocity increases with sort of omega square, and it decreases 1 by omega square at high frequency. This kind of experiment is limited within sort of 100 hertz or so. Okay. Now we can show that this, as expected in a nonlinear electrophoresis, the typical frequency dispersion having a maximum and with a limiting frequencies. And there are two the time scales involved here, tau p and tau e. Tau p is the basically the particle charging time, and the tau is the electron charging time. So therefore, if your time scales are beyond this, the particle will not respond, because you need to create this polarization of the charges so that particle can respond to that. Okay. Now, what is important is that if we look at that, the frequency dependence control, which I have shown, is possible when the frequency is beyond 20 hertz. What we see that beyond 20 hertz, that the velocity, both velocity Vx and Vy, are decreasing sort of with 1 by f or 1 by omega square, but the coefficient of the Vx is much faster than the Vy. Okay. Therefore, again, that when you change the frequency from one number to another number, since there is relative change in this component, and that is going to give you relative change in the theta. Okay. Therefore, the frequency dependent control is understood because the velocities are frequency sensitive. Okay. So therefore, we are sort of clear that the particle, the velocity around the particle is very, very sensitive, or the electroosmotic flows around the particle is very much sensitive to the frequency as well as the field. Now the question is, how do we understand this overall motility or the omnidirectional transport of the particle, and what is the role of this defect actually which we are talking about? Now this theory was actually sort of worked out by Sriram Ramaswamy from IISc and his student Sapnil Kole. So now what was done actually, let's say this is a particle and this is a nematic liquid crystals, and we're having a Shatterling defects, right? And when we apply electric field, we calculate the electrostatic force density. Okay, and I will not go into the detail. I will write the final expression and try to give you some physical meaning or the feeling about this mechanism, that why such particles are motile and why the direction dependent motility is appearing or occurring here. So this expression has two parts. This quantity in the first bracket in the beginning, this shows that the electrostatic force density of these particles having this kind of defects is dependent on the dielectric anisotropy, delta epsilon of the medium, conductivity anisotropy of the medium, and the Green's function, which are basically a positive operator. Now the sample which we have taken, liquid crystals, are such that the external electric field, such that the dielectric anisotropy is negative. Okay, therefore this quantity is positive. So the delta epsilon for our sample or liquid crystal is negative, conductivity is positive. Therefore, and this is a positive sort of operator, the whole quantity here is a positive. Therefore, the force, the direction of the force, okay, the direction of the force, right, or the sign of the force is actually mostly governed by the quantity which is given by this, the bigger the brackets in this quantity. What we see here is that the force density not only depends on the dielectric anisotropy, conductivity anisotropy, but also it depends on the curvature of the dialector around the particle. So this del theta del z and del theta del x, they sort of give the curvature of the director with respect to the x direction, and psi is the potential which is given by this expression where E0 is the applied field, and this is the lambda. The lambda is basically 1 for a conductor and is less than 1 for a dielectric. Now, sorry. So therefore, we can see that the electrostatic force density, it depends also on the curvature. Now the del theta del z is called splay. Splay means some kind of non-zero divergence of the director field, and del theta del x gives us the bending of the director field. So you can see there is a bending also. Of course, it depends on which plane we are looking at. But the point is that this del theta del z and this del theta del x gives the splay, means the non-zero divergence of the director field around the particle, and this gives the bend information about the around the particle. Also, there is a this del psi 0 del x, and psi 0 is given by this expression, and the electric field is there. So psi 0 is dependent on the field, therefore this force also is a quadratic to field. Now, so if, as I said, that the direction, or sorry, the sign of the forces, okay, sign of this force is mostly given by this quantity. So we should analyze the sign of these quantities here. So if you look at in the 4 quadrants, we can find the sign of this del theta del z, that is the curvature of the director of the what we call the splay, and the del psi 0 del x. So I will not go into details, but I will simply say that the sign of this quantity is given by in the bracket, okay, in the 4 quadrant, okay, and similarly del psi 0 del x is given in the 4 quadrant, this number. Now if you multiply this sign only, we can show the direction of forces in the 4 quadrants are given by these blue arrows around the particle. So particle is in the middle, and the direction of flows is given by the blue arrows. Now this is a kind of sort of a force dipole, because if you look at these flows, we can sort of treat this as equivalent to a force dipole, which is seen in a sort of kind of Stokes-Lit analysis. Now this arrow, this sort of says that equivalent direction of the force dipole, and this is called polar type. And if you look at this quantity, that means whenever I have a splay deformation, that is going to give me this kind of flow surrounding the particle. And again, this is symmetric flow, and this is called a polar type, meaning that equivalent to a force dipole whose directions are given by these magenta color arrows. Now, if we look at this part, that means if the region where I have a bend deformation, a bend, and that gives me a flow field around the particle, which is given by these blue arrows. Okay. Now, if you look at, this is like a typical sort of what we call a pusher type force dipole, and then the direction of forces are opposite. This is an equivalent situation. The point is that these blue arrows given are the direction of flows surrounding the particle in 4 quadrants. Now they are symmetric. This is what exactly happens when these chlamydomonas algae or even E. coli bacteria swim. You can see that the chlamydomonas are called polar because when they swim, with respect to the swimming direction, they pull the fluid towards them. And similarly, the E. coli bacteria, they actually push the fluid out when they are self-propelled particle. Because they continuously use the flagella and they beat in the medium to create local flows. The local flows are polar type for a chlamydomonas algae and it's pusher type for E. coli. The important point is that what we surprisingly find that these our particles in 2 different planes, wherever we have splay and bend, they can be either polar type, that means they can have this kind of motion surrounding the particle, or they can have pusher type motion, which is similar to a chlamydomonas or like a E. coli. This is fine, but if you have a silica particle, this flows will be symmetric. The particle will not move. But notice that our particles are asymmetric. They are genus particle. Therefore, the metal surface are highly polarizable. And I expect, so whenever I have a splay deformation, as I have already said, when you have a splay deformation, the flow fields are like this. That is, the flow is towards the particle. But since this left surface is a metal surface, this is highly polarizable. The induced flow on the metal surface is larger. Therefore, the particles will move, when you have a splay deformation, will move facing the dielectric surface forward. Look at this summary of the trajectories which I have already presented. If you look at the trajectories of the particle, trajectories of 3 and 7, you see the particles are moving facing the dielectric forward. And because if I look at this is the XY plane image, but in the XZ plane, the particle will have a splay deformation. XZ plane, okay. Similarly, in the YZ plane. So see, these lines represent the deformation of the liquid crystals around the particles, and red ring is the defect ring, and this is in the XZ plane. The XZ plane has a splay, so which I cannot show here, but I know that there is a splay deformation in the XZ plane, and this is what the XY plane I am seeing. Therefore, these flows are not symmetric anymore. They are a polar type, but this is the force dipole is off-centered, meaning the force center is moved to the metal surface. Therefore, this is off-centered force dipole, and it is a polar type, similar to what I have talked about in case of chlamydomonas. Now, if you look at in the YZ plane of this particle, in that case, so what will happen that we will see that this director field is actually coming out from the particle, but then if you go away, it is bending. So and then go into the actually plane of this. So they are bending. So these heads represent that they are gradually bending as you go away from the particle. There is a clear bend in this YZ plane, and when there is a bending, I have shown in the previous slide that this flow is pusher type. That means the flow is away from the particle, and in such cases, this flow, the particle motion is along this direction. Therefore, these two trajectories, look at the particle trajectory 1 and 5, the particles are moving facing the metal hemisphere. Therefore, it is therefore we can understand why this particle is moving, making the metal hemisphere forward, because this is dominated of the flow which is in the YZ plane, which is due to the bend. Now, in the intermediate trajectories like 2, 8, 6, or 4 can be understood due to a combined effect of the splay and bend. Okay. Therefore, all the trajectories I have shown in one of the summaries that there are all possible directions of motion you can imagine. We can transport the particle, and what is basically happening is that it is basically a competing or rather combined sort of effect of splay and bend deformation, which makes the particle either it's a puller type if it goes in this direction, or it is a pusher type in this goes direction, or it is both puller and pusher when they go in a diagonal direction. Okay. Therefore, the important point or the message is that the particles, the microswimmers here, the genus particles are sort of microswimmers whose local flows is similar to that of living microorganisms like Chlamydomonas or even algae, sorry, in E. coli. Okay. Now the question is, okay, this is what the sort of theory predicted, and this is what we explained. Now, is it possible to map the surrounding flows of the particle? This is extremely difficult experiment, because to control the orientation of the particle for a flow experiment is not easy. Still, I show you some sort of image where it is very clear that what theory proposed actually is consistent very much. I mean, or rather, the experiment is very much consistent to what is predicted in the theory. Theory predicts that yes, flow is stronger on the metal surface, and if you have a splay, then you have a sort of puller type motion which off-centered. Now this is the XZ plane. Since our field is always perpendicular to the plane, we cannot see the XZ plane. So what we did actually, we actually applied in plane field. Instead of applying out of plane field, we apply in plane field so that we can actually mimic what is happening in the XZ plane. Then we put some quantum dots and apply field. We can see the metal surface is highly polarized, and flow of the particle, the flow, surrounding flow around this metal hemisphere is much stronger. Okay. If you look at the direction of the flows, also is matching. And of course, slightly the particle is tilted. Nevertheless, we can clearly see the direction of motion of the metal surface is sort of similar what is shown in the or predicted in the theory. And you can see that flow direction on the dialectic hemisphere also is consistent what we see in experiment. Therefore, that at least in the XZ plane, we can show the surrounding flows which break the symmetries, and also it proves that it is off-centered force dipole as predicted in the theory. Now, how much time I have, Jadisman?
You still have 10 more minutes.
Okay, fine. I will finish it. Now, another, okay. So now another important sort of aspect of that. So as I told that there are, in principle, actually, we can induce different types of defects, even with spherical particles, okay? And for example, this is a genus particle with boson defects, half defects. And as we can see that orientation of the molecules is parallel to the surface interface. So when we disperse such particles, and what happens? So I have basically joined in this movie some short clips and then combined to show the effect. So the field is perpendicular to this plane, and this director is in this direction given by this arrow. Now you see when I apply this field, what happens? The particles are actually moving, but what is important point to note that in all trajectories, metal hemisphere is always forward. Unlike in case of quadrupolar particle, that sometimes in the previously I have shown that it was going metal hemisphere forward or dielectric hemisphere forward. But in this case, the motion of the particle is such that always the metal hemisphere is forward. And if you look at this sort of summary, again, we define a genus vector, and in fact, we can have all kinds of orientation, and we always find that particle moves, keeping the metal hemisphere forward. And these are actually a purely pusher type particles. Okay. Again, the similar sort of theoretical analysis can be done, but what we realize at this moment is that the linear theory which we have used doesn't work anymore here. But sort of from the experiment, we clearly say that these are pusher type particles. But yes, we have to use a nonlinear theory, which is really now it's not so easy as of now, but it's doable. And mostly it has to be done numerically to show that they are actually pulsatile. The point is that to summarize, what I have said is that if you have a dipolar particle, genus particles, they have a bidirectional motion, either they go left or right. And if you have a quadrupolar particles or boson particles, if they are non-genus, they are not motile. But the moment you make them genus, the particles become motile. Not only they are motile, we can also control the direction of motion at will, which is very, very important for targeted delivery or transport. And the mechanism of the swimming is basically sort of similar to what is seen in case of a living microorganism. I mean, they are either polar or pulsatile particles. Okay. Now the question is, suppose I have many particles, then what happens? Okay, that is really messy, and I will not go into detail. But let me show you some interesting effects on a pair of particles. So these are the two genus particle having quadrupolar defects, means they are dressed with ring defect. Now you see this particle half metal dielectric interface I can see. For this particle, dielectric surface is down. So what I do, so I apply some fixed frequency and increase the voltage, okay, from 0 to 1.6. Now what you see, please look at carefully, the particle first rotate. Metal surface and dielectric surface, now you can see it clearly. As we increase the field, you see the interparticle separation actually sort of increases, okay? And they have some equilibrium until some field. But if you increase the field beyond some value, they completely actually go away. They start actually swimming based on the phenomenon which I have described. Okay. Now, if you see in this, let's say, sort of few snapshot, what is happening at zero field? Yes, the metal dielectric hemispheres are randomly oriented, but the moment you apply some field, I can clearly see that metal dielectric interface is becoming parallel to the field because field is out of plane. Okay. And with increasing field, they tend to go away, the interparticle separation decreases. So what is happening? So to understand what is happening, we took two genus particles, two non-genus particles, these are two non-genus particles, and apply field, and we measure the separation as a function of field. What is interesting is that we see for a non-genus particle, the interparticle separation does not change. Okay, they cannot be separated by field. But for a genus particle, they are separated. Of course, this happens in this explained in the low field region, because in high field region, they will be totally separated and they will be a typical microswimmers. But we are working much below that voltage. The point is that they have interparticle separation basically increases for genus particle. What is happening? The moment you apply electric field, the metal dielectric interface, they induce some sort of dipole moment. Okay, the induced dipole moment is parallel to the field. That is why the interface rotates. Okay, and it is known that for a genus particle, the induced dipole moment by the field is parallel to the interface. Therefore, the particle rotates because they induce dipole moment. Now, and initially the two particles were bound in the liquid crystal medium because of the elastic forces. The elastic forces, we know how much the forces, what is the typical binding energy. In fact, typical binding energy of these particles are few thousand kBt, okay. And now, so they are basically when you apply field, they become a dipole. Now, two parallel electric dipole, they with increasing field, they repel each other. So what happens now is that what we found is that the moment you apply electric field, then they induce a dipole. So P is the induced dipole moment parallel to the field direction. Now, elastic, initially they were bound due to elastic forces. Their binding energy was few thousand kBt, but the moment you increase the field, there is a Coulomb repulsion. Therefore, the Coulomb repulsion it takes over and it works against the elastic attraction. So, because of the Coulomb repulsion of the two parallel dipoles, they go away from each other. Now, if it is the case, then we should be able to estimate the dipole moment. So to estimate the dipole moment, what we did to check that this sort of the explanation it works out. What we did, we know, okay, if there are two parallel dipoles, we know typical what is the electrostatic or the Coulomb repulsion between two dipoles, which is given by this expression. where R is the separation between the two dipoles. Now at equilibrium, so what I was saying here, okay, let's say when I have some kind of separation here, at equilibrium, the elastic force is balanced by the Coulomb repulsion. Okay, now so this is the this Coulomb repulsion, the force Fd, and which is given by this expression. So P is the induced dipole moment, and epsilon m is the dielectric constant of the medium, and this is equilibrium separation, which depends on the field. Now this is, since it is under this system is under equilibrium with the elastic forces, and therefore I can actually equilibrium distance R we know, and if we know this force, elastic force between the particle as a function of distance, we can find out the induced dipole moment. So using this expression and knowing that field dependent R and this sort of elastic force we know of the particle, which is measured just now without any field. So what happens? How do we measure? We take two particles at far distance and we allow them to slowly approach. You can see because of elastic attraction, they come and then they sort of join. And assuming that there is no acceleration, the viscous drag force is balanced by the elastic forces. Okay, and therefore this drag force we can measure by integrating by knowing the velocity of this thing, and since frictional coefficient also we know, therefore we can calculate the elastic forces. You can see as a function of R between the two particles. So from this force and the equilibrium separation R, we can actually calculate the effective dipole moment P effective as a function of field, and we can see it's linear. Okay, and it passes also through the origin. Therefore, the induced dipole moment is merely due to the field, which is proportional to the E, and we can also measure this what is called polarizability alpha, and this at least 4 different frequencies we measure this polarizability, which is given in this this red symbol, and we can see the polarizability decreases with frequency as expected. Now see that of course then another question that what about the hydrodynamic flows which are there surrounding the particle? Do they have some role? We actually calculated, I will not go into details, then we calculated what is the hydrodynamic forces the particle can experience due to the local flows. In fact, we find that that is almost 1/10 of the comparable to this the electrostatic, the Coulomb repulsion. Therefore, hydrodynamic effects are there, but they are negligibly small compared to the Coulomb repulsion. In fact, to calculate this, so this is experimentally measured the polarizability. So we said, okay, so we can, since this is a sort of dielectric particle, we can calculate theoretically the polarizability using this expression where the alpha is the polarizability, M stands for metal because it's metal dielectric, and D stands for dielectric, which is given by this expression, where A is the radius of the particle, and K is the complex cross-osmoticity factor. And the sigma, it depends upon the frequency, electric double layer around the particle, sigma and size, all kinds of these numbers can be easily sort of measured, and in fact we have measured for this number for this particle. Putting all this number in this, and we calculate this alpha for metal and dielectric, and if we take this sort of mean value of them, and we can see the theoretical value is sort of comparable to that, to what is measured in the experiment. So the point is that this competing effect of this elastic interaction and Coulomb repulsion between this field-induced dipole gives rise to some sort of competition, and from that, more importantly, we could measure the induced dipole moment of the particles. In fact, I do not know if any other experiments so far have been able to measure the effective dipole moment of genus particles. Okay, this is extremely simple sort of technique, but it is very powerful because that you don't need much things. You just need to really make the particle and apply the field and track the particle and calculate the relevant parameters. So therefore, this is a very effective and sort of, I would say, sort of a new way of measuring the induced dipole moment for such complex particles. Okay. Now, to summarize that, what I have talked about, actually, we have actually created a controllable active particles. Those particles, they acquire motility and due to this sort of imposed electric field. And not only that, we have shown that this motility of this particle is controllable. That is the most important sort of aspect of this study. And therefore, we can control the trajectories at will, and we can pilot and as we want. And therefore, this is very, very useful for controlled transport. Now, if I have large number of particles, and where we have this, we have a we will have hydrodynamic interaction, elastic interaction. We have also electrostatic repulsion. It's a very complex interaction. But the point is that it will be interesting to study their collective dynamics of a large number of such particles in the, I mean, from the point of active matter thing. Okay. So in fact, what we found is that I have only talked about so far the spherical particles and of course the genus particle. But we know we can imagine, all kinds of particles with different asymmetric shapes and also making them genus. Okay, so we have actually, we feel that we have opened up sort of unexplored direction where the defects of this liquid cell medium and symmetry of these particles and the electrostatics. So using all this, exploiting all this, we can make a complex system where not only we understand the motility of the individual particles, which are useful for control, transport, drug delivery, and so, but their complex dynamics also will be useful from the active matter point of view. Okay, so with this, I think I will stop here, and I would like to thank, of course, DST for this funding of this experiment. And all the experiments were done by my student for his PhD thesis, Dinesh Kumar. And the theory was worked out. This basically the force dipole, which I talked about, was Swapnil Kole is his Siram students, and they together sort of did this calculation. Thank you for your kind attention.
Thank you very much, Surajit. Thank you for this wonderful talk. I will like the talk to be open for more questions. Yeah, Sushil.
Yeah, thanks. Surajit, I have a few queries. Okay, maybe I'll go in queue with other people. Well, the first one is one clarification about the structure of this Janus particle. Okay, you start off with a silica particle, which is obviously spherical.
Yes.
And then you coat the titanium metal on half of it, which is about 35 nanometers of layer.
Yes.
And then you again coat it with a silica layer.
Yes.
Correct?
Yes.
How do you ensure that the final particle is actually a sphere or is not a protruding hemisphere on one side because of titanium?
Yes. Okay. So if you look at that thickness, let me go back and mention the thickness. You see that the particles are having diameter nearly 3 micrometer. Okay, and we give a 35 nanometer titanium. Okay, and then on top we also put a silica. So yes, you can say that there is the one side of the particle is around 35 plus 10, 45 nanometer. But compared to the size of the particle, that is extremely small. So therefore, that does not really sort of break the symmetry of the particle. Still, we can consider that this is a symmetric, self-symmetric particle. Okay, yeah, because in fact, even if you have a sphere, this if you look at the surface profile carefully, even 30-40 nanometer is obvious. Even for the surface profile will give you non-uniformity in this one in the silica particle. So therefore, this is not really that big compared to size of the particle.
Yeah. Okay, thank you.
Are there any other questions? Okay, Sushil, if you have further questions, you can.
Yeah. Thanks, Jyotishman. I'd just like to continue. Okay, a couple of slides I would like to go back. Slide number 11. You compare the next slide, very next slide. You compare the velocities. You see, there's a crossover at 3.5 volts. Is that genuine?
Yeah. No, actually, it is. See, these particles. What happens is that there is no crossover as such. In fact, I don't take it seriously. This is because these particles, if you see that the field does not start from zero, right? So there is a minimum field which is required to pump the fluid enough to the enough velocity such that they become motile. It happens that in the experiment, you see, if you put the experimental error bar, you will see actually, I mean, this straight line is given because to the feet, to fit it. That's why this looks like, but actually, yes, they are not.
Okay, because that would have a very strange implication.
Yes. Any crossover will have a definitely.
So the one last point is on slide number 23. You estimated the polarizability. Okay.
Yeah.
Now the polarizability goes by the volume of the metal content.
Yes.
Okay, and what you have is a very thin metallic shell.
Yes.
Correct.
Correct.
So if I look at the agreement or disagreement between theory and experiment.
Yes.
Do you think that shell is an issue there?
Yes, you are very right, and it's a very important point I think you have raised, that this is a very approximate calculate. And in this calculation, we have assumed, see how we have calculated. We have assumed that it is a full dielectric or it is a full metal, right? And we have taken this half contribution from each. But actually, it is not a full metal. It is actually a thin layer of the metal. Yes, that way, that is why you see the agreement. I mean, is not as good as you see in the experiment. So this disagreement, what you see in the experiment, yes, it partly could be due to that effect which you are saying, because the theory is very, very crude. And apart from that, as I said that the hydrodynamic flows between the particle, right, will also have some influence on the interparticle separation. But though I have calculated roughly, we found that it is almost 1/10 of the force which we get due to the Coulomb repulsion. But still, that in fact, when you increase the field or so, it may have some contribution. Therefore, this disagreement, yes, definitely is due to that that approximation which is used in the calculation. Yeah. Right.
Okay. Thank you very much.
Surajit, I have a quick question.
Yes.
Can these systems be then used for some purposes of delivery of say molecules?
See, theoretically speaking, this is yes, this is a sort of controlled transport. Therefore, you can use it for delivery, targeted delivery. But the limitation is that this experiment is limited to the liquid crystal.
Yeah.
All this beautiful thing we see, all in the liquid crystalline phase. The moment you hit the liquid crystal and go to isotopic state, nothing is seen. You don't see. You just see a normal electrophoresis, and this particle will not move if it is a non-genus particle.
Yeah. Okay. So, but where do you envision these things could be useful in some practical application?
It's a difficult question, but yes, but one thing, many of these allotropic systems,
right?
The biological systems are allotropic. They are also anisotropic, right?
Right.
So many of these biological systems, they are allotropic and they are anisotropic. Yes, there is a possibility that this can be sort of used there, and you can have a control. Let's say you can have sort of a control reaction, for example.
Okay.
Right? You can have two. In fact, not only this, I talked about a particle, solid particle, but in fact, you can have a liquid droplets, right? Of invisible liquid droplets.
Yes, you can move the droplets.
Points, and you can guide them to control and have a reaction in some place.
Yes. So that has been shown. That has been,
yeah. So, but here I'm saying that in liquid crystal also it should be possible. It should be possible to do that.
Okay.
Control reaction in a desired, or destination or place.
Okay. Fine. So, any other question for Professor Dhara? Well, if there are none, I would like to thank Surajit again, and thank you for actually making sure that we have the colloquium, and I'm very happy that Sushil suggested your name. Of course, we would have anyway had you physically here, but thank you for doing the webinar series. Hopefully, at some point of time, you can physically visit us.
Yes.
And
thank you, Sushil and Angsuman both. Nice to see you after a long time.
Right. And so you can take a break. I'm going to stop the live streaming, and then you can make this as a meeting with Sushil, and then Sushil will take you to the lab, virtually.
Okay. So I will stop sharing this screen now, or?
Yes.
Okay.
Thank you very much.
Okay.
And I would like to thank all of you who joined us today for this session. And just a reminder, next Wednesday, we are going to have Professor Ullas Kultur speaking to us about his latest research from his lab in TIF. So thank you very much. I formally close this session. Okay, I want to thank Rajesh Mistry for holding up the lecture theater broadcast.